All right, we're going to look at electrostatic equilibrium today. Electrostatic equilibrium, the whole idea of the equilibrium is the sum of the forces equals 0 at that equilibrium point. Now, what's kind of interesting about this point, when we do it with this charge and forces, the charge at the equilibrium point is arbitrary. It doesn't matter. It can be positive, it can be negative, it can be big, it can be small. It doesn't matter. So what we'll do is we'll typically call it a test charge. And I'll typically choose positive just for consistency purposes. Now, these problems do get a little more difficult when we want to find the equilibrium point. If it's find a charge so that point becomes equilibrium, we're summing up our forces and solving for charge. If I'm trying to find a point, we got to go through two processes. One is we got to know where is it going to be, and then two, we got to solve for it. Okay? The reason we have to do this first step to figure out where is it going to be is because in the end we're going to solve a quadratic, so we're going to have two solutions. And so we got to know which solution we want. All right. So what we have is we have two like charges. Where is the equilibrium point going to be? All right. So let's take my test charge, my little positive here, and if I put it in the middle, you're going to see that both charges are going to repel it. This charge, I'll call it charge 1, is going to repel it this way. Charge 2 is going to repel it this way. All right, so we could have equilibrium in the center. Okay, if I put it over here, both charges are repelling it, so both charges are pushing it this way. And just to show you that the sign is arbitrary, if I flip it to a negative sign, both charges attract it now here. And in the middle, both are attracting it. So instead of F1 pointing this way, it's pointing this way. Instead of F2 that way, it's pointing this way. And so charge sign doesn't matter. Also over here, we're going to end up with the same thing. They're both going to repel it or they're both going to attract it. So our equilibrium point is somewhere in the middle. Now, in order for those forces to balance, it's got to be closer to the smaller charge, because the closer the two charges are, the larger the force is. So if I have a larger charge, it's going to be producing a larger force. So maybe this is 5 microcoulombs and this is 2 microcoulombs. So my equilibrium point is going to be a little bit closer to that 2 microcoulombs so that those two forces are equal. So whenever you see same charge, know that the equilibrium point is between the two charges and it's closer to the smaller charge. Okay? So what happens when we flip it, when we have opposite charges? So if we stick it in the middle, this one is attracting it, this one's repelling it, so both of them are trying to force it that way. So the middle doesn't work. So what you end up with is you end up thinking about what happens outside. So in this case, it's getting repelled by this one, but attracted by this one. So this could be an equilibrium point. Over here, it's getting repelled by the positive, attracted by the negative, so it could be equilibrium over here. But which is it? It's outside, but which one is it? And again, we'll go with that same idea that this is 2 microcoulombs and this is negative 5 microcoulombs now. So it's going to be outside, but it has to be closer to the smaller charge. So when we have opposite charges, the equilibrium point is going to be outside, and it's going to be on the side of the smaller charge. Once we've identified the location of it, then we can set up our problem. And so our problem setup has 4 parts to it. The first part is we need to choose one of the charges as the origin location. Okay? Then we need to define the distance from the origin to the equilibrium point as r. We need to find the distance from the other charge to the equilibrium point in terms of r, and then we can set up our summation of the forces and solve it. So let's set this problem up. So now we're going to solve this problem. We have a 5 microcoulomb charge and a negative 3 microcoulomb charge, and I want to find where is the equilibrium location if they're separated by 0.3 meters. So I see that they have opposite charges. That tells me my equilibrium point is outside, and it's going to be on the side of the smaller charge. So 3 is smaller than 5. So that means my equilibrium point is going to be over here. Okay? So first step, I need to choose one of the points as the origin. So I'm going to choose this point right here as x equals 0. So I've chose that point as the origin. That puts this point, which is separated by 0.3 meters, at x equals 0.3 meters. I now need to define the origin to the equilibrium point as r. So that means this distance right here is r. Okay. Now I need to define the distance from the other charge to the equilibrium point. So what's that going to be? Well, if this whole distance is r, if I subtract 0.3 meters, I'll be left right here. So this is going to be r minus 0.3 meters. This is an essential step. Okay. Then we're going to sum up our forces, set equals 0, and solve. All right, here we go. So what forces are acting on our charge over here? Well, I do have an attractive force from charge 2, so I'll call that F2. I have a repulsive force from charge 1. I'll call that F1. So now when I sum up the forces at my equilibrium point, I'm going to get 0. So I have F1 minus F2 equals 0. Set those equal, so F1 equals F2. And now I'm going to make my substitution using our force between two charged particles. So I have K times the two charged particles involved for force 1, which is going to be charge 1 and my equilibrium charge. Because it's arbitrary, I'm just going to call it capital Q. Okay. Divided by the distance between them, which is r, between charge 1 and my equilibrium point. My second force is going to be involving charge 2 and this one. So it's K times Q2 times my charge at my equilibrium point divided by their distance squared, so r minus 0.3 squared. And what we see here is we see that the k's cancel and the q's cancel. At this point, we're just solving now. I know what Q1 is. I know what Q2 is. I just have to solve for r. Now, you'll notice that we are going to have a quadratic to solve. So the easiest thing to do to get it into more of a quadratic format is to do a cross multiplication here. So I have Q1 times r minus 0.3 squared equals Q2 times r squared. And so if you want, you can go ahead, FOIL this, distribute, get everything into a nice polynomial, use the quadratic equation. If you want, you can, if you have the graphing calculator that's color, you can just plug this equation into your solver. If it's an older calculator, you got to subtract that over to the other side so it's equal to 0 and plug it in your solver. Now remember, there's two solutions. Okay? You want the solution for r that is greater than 0.3. Okay? So when you do this, plug it in your calculator, you are going to get an r value of 1.33 meters. Okay? Now, here's a cool little trick. What happens if these were the same charge? Okay. So what would happen if these were the same charge is I would have my equilibrium point somewhere in the middle. Okay, and closer to the smaller one, I'd have r, and so then this distance here would be 0.3 minus r. Now what do you notice? I went from r minus 0.3 to 0.3 minus r. They're kind of multiplied by -1. And what happens if I multiply the inside of a square by -1? Does it change anything? No. And so I end up with the same equation whether they were opposite charges or like charges. And so the other solution to our quadratic is if they were the same charge. Okay? But make sure that you find the one you need, and you know the one you need based on if they're the same charge or the opposite charge, you can figure out where it is. There we go.